Welcome back. In the last video, we had made three-phase source with three-phase VI measurement block and a scope. Today we will see how this scope works and how the values are calculated by using these graphs. So this is the output of this three-phase source. The parameter we set was 400 volts RMS and with frequency 50 Hertz. So let's see what is the output. So this is the scope. The scope has different parameters to change the vision of the graph. First of all, we will press the scale X and Y button and select the horizontal axis, and then the zoom button with the second option, zoom X. So when we are doing this, then the graph is coming out to be a triangular graph. This graph should be a sinusoidal graph, so we will check what is the problem. So we should remove this extra graph and there must be a load. We will add a three-phase load in it, RLC load series. So the value of the three-phase source is 400 volts with load flow analysis as a swing. There are three options in the swing: PV and PQ. PQ means you have to provide the active power value as well as reactive power value. For example, if you want to design a generator with having active power of 10 kilowatts and with reactive power of 5 kilowatt exponent 3, then it will become a 15 VA generator, volt current. So 15 VA generator will be designed by using 10 kilowatt active power and 5 kilo VAR reactive power. So we are saving this. Now we run the system again. Now let's see, the graph is now okay. We are having a pure sinusoidal three-phase supply, and if you see the peak of this, the peak is still some irregular shapes. 320 peak to peak, the peak of the waveform is coming. So there is some transients in the system. We can check why it is coming again. In the three-phase VI measurement block, we have two options, voltage measurement options, either phase to ground or phase to phase. We will put it as a phase to phase measurement and save it. We run again the system and check what changes have been now coming. So now the waveform is better than the previous one, but still there are certain issues in the harmonics in the waveform. So we will check the load. The three-phase serial RLC load has nominal phase-to-phase voltage of 400 volts. It should be 400 volts because the generator is working at 400 VRMS with a nominal frequency of 50 Hertz. The active power of the load should be less than the generator, so it can be 5 kilowatt. However, the reactive power of the system can be 1 kilowatt positive and 1 kilowatt negative. Now we save the changes. The configuration is Y, grounded, load flow, constant Z. Now we will save it, and the configuration here should be Y and ground. The generator should be grounded to avoid any harmonics in the system. Now we will run the system again and check the output. Now the system has the same variations. We have to find out what is going on, why the shape of the waveform is not as per the required waveform. If we ignore the reactive load, then the negative reactive load, we have to avoid this negative reactive load, then the capacitor will be disappeared from the load. So the negative load is basically the capacitive load, and the positive reactive load is basically the inductor load. If let's say we ignore the capacitive load and then see the behavior of the waveform, we will save the system and then again we will start the system. Still there is a waveform problem. So in order to make the output discrete, to have a continuous waveform smooth, we will go to the model settings. Then we have here the solver is a fixed step solver. So we will change the fixed step to variable step and select the solver ODE, ODE 23, or you can use any of the solver for the solution of the parameters of the blocks we have used. So ODE 23, we will use it in this simulation. It will apply, and we will change the power GUI to discrete. The simple time is over here is 50 exponential minus 6, 50 microseconds. Now we will run the simulation and see what is the result coming now. So now we have the result with pure DC, with pure sinusoidal, and the waveform is now smooth as compared to the previous one. So here we will see the peak, how much peak it is giving. It is giving the peak of around 560. The peak of the output is around 560 for the voltage waveform and 110.5 for current waveform. So what does it mean? Why it is coming 560 volts? So we have this value as a peak voltage. We have set the parameters. (400 volts VRMS). So if we change the 3-phase VI measurement to phase to ground, then let's see what the output comes. Now the output is the required output which we want. The waveform has now 300 volts, 305 volts peak value, and the peak to peak value is around We have set the face-to-face value of 400 VRMS, and the peak is now coming to be around 305 VRMS. So we will see how it is coming. For example, we have set our VRMS peak to peak to 400 volts. So in order to find the phase value, so V phase will be 400 divided by root 2. So here we have a VRMS of 400 volts. When we will divide the 400 with root 3, we will get 230.1 volts per phase. This is the per phase voltage. If we want to find the V peak of the signal, then we will multiply the 230 volts with under root 2, and it will come around 325 volts peak. So our waveform should have 325 peak value and 230 volt per phase value, and with 400 volts RMS value. So we will go to our scope and see that how much the value is coming. So we have the peak to peak voltage here will be 400, but the peak value of this waveform will be should be around 325. So when we look at the waveform, then the peak is around 325 volts as per the formula of peak voltage. So this is how we confirm our waveform, that is it as per our given requirement or not. So in short, we have to summarize the whole circuit, we have the three-phase source of phase-to-phase voltage VRMS 400 volts with 50 Hz frequency, and we have connected the three-phase VI measurement block with parameters of voltage measurement as phase to ground and current measurement to ES. After that, we have connected a three-phase series RLC load with active load, resistive load of 4 kilowatt and the inductive load of 1 kilowatt, and then the scope. Thanks for watching the video.